assistant professor at Department of Electronics in CUSAT. And it's my privilege to introduce him. He being the coordinator was instrumental in making sure that you get an excellent set of resources. So he did his BTech from NIT Calicut and has worked as system engineer in Wipro. He has completed his MTech from IIT Delhi and has joined Broadcom Bangalore as ASIC engineer. In 2012, he joined as research scholar under Professor S.K. Nandi at CAD Lab in ISC Bangalore and received his PhD in 2018. He has more than 7 years of experience in the domain of embedded systems, ASIC, and FPGA design, and his academic and research career spans over more than 12 years. So his research interests include AI edge, neuromorphic computing, and hardware accelerators. And he has also published multiple papers in leading international journals and supervised multiple projects. It's my privilege to introduce Nalesh and welcome Nalesh to this FDP. Over to you.
Yeah, thank you, Dr. Tripti, for that introduction. I'll start sharing my screen. Is my slide visible?
Yes, Nalesh.
Just a second. I'll stop the video for now. Yeah. Good evening, everyone. So the title of my session is hardware for artificial intelligence. There is hardware for artificial intelligence. So the objective of this session is to take you through the basics of implementing artificial intelligence on hardware. So basically, what is the need for specialized hardware for artificial intelligence? Mainly deep neural networks. And then what are the different platforms? I'll briefly go through what are some of the architecture and algorithmic optimizations available, and some of the platforms, if time permits, we will cover. You can consider this session as a precursor to the later sessions coming up in deep neural network accelerators, compute in memory, etc. So with that, we'll go to the session. So these are the topics which I am planning to cover. I'll start with basics of neural networks and deep neural networks, go into convolutional neural networks, why specialized hardware is required for deep neural networks, some of the architectural and algorithmic developments which can be done to make neural network deploy on some of these specialized hardware. And I'll give a brief introduction to compute in memory because that is one of the upcoming, like one of the interesting domains coming up for neural network accelerators. And we have a session on that. This is my plan. So this gives an overview of what exactly deep learning is. I am sure that most of you know are aware of artificial intelligence. So if you look at it, deep learning is actually a subset of the larger domain of AI, which has this machine learning and artificial neural network. Deep learning is a subset of this. So what are these artificial neurons? So they are based on what are known as artificial neurons. Which are modeled based on the neurons available in nature. We can see that the basic biological neuron, it has what are known as these dendrites and axons. Similar to that, artificial neuron, we have so the dendrites in biological neuron, the inputs come through the dendrites, and the outputs are triggered through the platform. So similarly here, we have multiple inputs coming in, and some calculations are done on the input, and an output is generated. And what are these calculations? So each input will be multiplied with a weight. So if you consider input x0, you have a weight w0. So you have w0 into x0. Similarly, each of these input, which will be coming from another neuron, so it will be multiplied with a weight, and these are all added up, and a bias is applied, and then the output of this, so the after multiplication and addition, the output is a nonlinear function is applied to the output. This function is called the activation function, and uh, uh, that will generate the output. So this model is called the perceptron model, which forms the basis of most of the artificial neural networks. Uh, so uh, 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 so how can you build a neural network using this perceptron? You can have what are known as single layer perceptrons, where you will have only a single layer of neurons. So these the white dots are all neurons. You have only one layer of neurons, but the problem is these are very limited in functionality. They can be used only to learn functions which are linearly separable. I won't go into the details of this. Those who are interested can look at it. Because of this limitation, multi-layer neural network was introduced, where you have more than one layer of neuron. So you have the first layer, which takes all these inputs. These inputs are multiplied with the weights. The output of the first layer is passed on to the second layer. So you have multiple such. So these multi-layer perceptrons, they were able to learn linearly inseparable functions also, but non-linear and very complex representations, this was still not able to learn, and that is when this activation functions has been introduced. Many different activation functions are there. Um, Linear activation, logistic activation, ReLU, TAN, H, etc. So this is the perceptron model. How is this applied? So, for example, consider this a handwriting digit recognition example. So the application here is you have a digit which is handwritten, and we have to recognize the digit. So the digit will be in the form of an image, and image, as you know, will be consisting of pixels. So here we are considering a 16 by 16 pixel. So what is our objective? Our objective is to identify a digit from this image. So the digit can be from whatever from 0 to 9. So we have 10 possible outputs. What are the inputs? The inputs are 16 by 16 pixels, that is 256 pixels. So we have 256 inputs, and what are the outputs? So in a neural network, the neural network don't exactly say what is the whether it is number 2 or whether it is number. Instead, it gives a probability of each possible outcomes. So for example, what it says is, here it says there is a 0.1, so 10% probability it is 1. There is a 70% probability it is 2, and there is a 2% probability it is 0. So like that, the neural network will be giving the outcomes in terms of probability. And if one of, so here obviously, since the digit is 2, and the neural network is able to say with 70% confidence that the digit is 2. So that is how the network works. So how exactly this? How is this model? So we have 256 inputs, which is passed on to the neural network, and it should generate 10 the outcomes for, or the probabilities for 10 different outputs. So starting from 0, for example, y1 can be the probability for 0, y2 for 1, etc., and y10 for 9, or something like that. So basically, we will have a function which maps from these 256 inputs to these 10 outputs. And this function will be a neural network, which we saw earlier, which will have multiple layers of person. But what has been found was, like, instead of having very few layers in between, if we add more layers between the input and output, there is the accuracy or the performance of the neural network was found to improve, and that is when this deep neural network was the evolution of deep neural network happened. So basically deep neural network means the basic idea is to have many hidden layers between the input and the output neurons. How does it work? So you will have some inputs. So here the inputs are 0 and 0. Each connection is a connection from an input to a neuron. So it will be each connection will have a weight, which we call synapse. So the weight will be multiplied by the inputs. So here this neuron will have the top neuron in the first layer has input is connected to both the inputs. The first input is multiplied by 1, the second input is multiplied by 2. So the result of this is added, and then there will be a bias also applied, and a nonlinear function is applied. Similarly, the bottom neuron, it also has is connected to both the inputs. So here again, it is multiplied by -1 with the first input and 1 with the second. So like that, the layers are connected. So if you look at the operation, what you will have here is the weights. So if you consider the first layer, you have the weights 1 and -2 for the first neuron, -1 and 1 for the second neuron. And what are the inputs? 1 and -1 for the second input. What are our operations? 1 into 1 minus 2 into -1. For the second neuron, it is -1 into 1 plus 1 into -1. So this can be expressed as a product of a matrix and a vector, where the matrix will represent the weights and the vector will represent the input. So plus the bias, if any, you can apply, and then sigma is the nonlinear or the activation function, which is applied on the result. So here the result of this matrix multiplication plus addition is 4 minus 2. So we apply the nonlinear function on it, and you get the out. So the neural network operation basically can be reduced to matrix operation. So that is the takeaway from this. Each layer you will have such matrix operation. So you can see the first layer W1, which is the weight matrix for the first layer, into X, which is the input from the inputs, plus B1. So its output will be passed to the second layer, where it is applied, which is represented as A1 to the vector A1. So the weight for the second layer is in the matrix of W2 into A1 plus the bias for the second layer B2. So basic. So this is the matrix representation for the neural net. Coming to so here we were talking about general neural network. So there is the one of the most common used neural network is the convolution neural network, which finds applications basically in the image domain. So what happens in convolution neural networks here? The connection is slightly different. So we have we'll be going in detail. So we will have a series of layers called convolution layers and other layers. So for example, what we have here is a convolution neural network, which takes an image as an input and try to identify what is the object in the image. So this is a image classification example, a CNN, which is built for a image classification example. The initial layers, which will learn the features from the image, and the last layers, based on the features, it will try to classify the image as based on whatever is the content of the image. So what are these convolution layers? So a convolution layer, so typically, as we saw earlier, each input will be multiplied with a weight and added to generate the next layer. So the neuron in the next layer will be taking inputs from all the inputs from the previous layer, multiplying with weights, and add them up and give the output. But when we come to image, for example, consider a typical image, RGB image, which has of 32 by 32 pixels. So remember that each pixel will have R, red, green, and blue component. So each image is 32 by 32 into 3 size. So those many inputs are there. So 32 into 32, which is 1024 into 3, so around 3092 inputs are there. And each of the input, if we try to multiply with a weight and then connect to the next layer, the amount of computation is going to be too huge. That is one thing. The second thing is, we know that images have some spatial properties, like the neighboring pixels in an image, they are not completely independent. They have some properties which they have some dependencies which gives uh, uh, which carries many information about the content of the image. So that is the reason why, instead of having a normal fully connected neural network, we have for images what are known as these convolutional layers. So in convolution layers, what we will have is, we will have what are known as filters. So the filters or kernels, they will be of some fixed size. They will typically be less than the image size. So typical sizes are 5 by 5, 11 by 11, etc. So you will have these pixels. So the operation, if you see here, so the inputs, which are the input image here, the filter, you will have the filter, and the filter will be sliding over the input, and convolution will be applied, and output will be generated. So what is convolution? So convolution, as you know, you multiply the so if you have vector A and vector B, so you have A1 B1 plus A2 B2 plus A3 3. So that operation is the convolution operation. So here, if you see here, the first in output, how are you generated is, so 0 into, so 0 plus 1 into 1 plus 2 into 3 plus 4 into 3. So that is 90. So that is the first output. How is the second output generated? Now the filter will slide. It will slide to the next set of inputs, that is 1, 2, 4, 5, and you will get the output 4, 5. Then the filter will slide downwards. So now you will have 0 into 3 plus 1 into 4 plus 2 into 6 plus 3 into 7. So that is the third output, and you will have the final output. So this is the convolution operation. So convolution, it is a dot product between the filter and the small chunk of the image, and the filter will slide over the image to generate all the output. So this is what happens in the convolution. And when you have so each layer will have more than one filters, and each of these filters will generate outputs. These outputs are known as the activation maps. So depending on the number of filters, there will be many number of activation maps. So so convolution neural networks are a sequence of such convolution layers which have many filters, which are going to slide over the inputs and generate the output interspersed with. So each convolution layer will be followed by an activation function, similar to what we have seen earlier. So activation functions are nonlinear functions. So each convolution layer will be followed by activation functions, and there are certain additional layers known as pooling layers and fully connected. So if you see, for example, the image classification example, so you have convolution layers and ReLU, which is a activation function, followed by another convolution layer, another activation function, then a pooling layer. So like that, you have a series of layers, and finally you will have the fully connected layer, which will give the a final output. So if you see, each of these convolution layer will be learning some feature from the image. So each of these convolution layer will be learning some feature. What those features are, we won't go into the details, but we are interested in the computational aspect. So if you see, the parameters or the weights. So compared to the normal neural network, so here if you see the each convolution, the weights are only 5 by 5 into 3. So for example, here 15 into 3, 45 values constitute the weights. So compared to the input, you have only some 45 weights, but you have more such filters. So depending on the number of filters, your weights increase. So convolution layers, so weights or parameters, if you see convolution layers are some, it will have some amount of weights which are given by the filter size. Whereas pooling layers, we'll see what the pooling layer is. It will have no weights. And finally, the fully connected layer, they will have lot of weights. So if you compare these three layers, the convolution layers will have some amount of weight. Pooling layers will have no weights, and fully connected layer, lot. What is pooling? Just to introduce you, we are not going to look into pooling later. So basically, it is a downsampling. It is called the pooling or the subsampling layer. What you will do is you will reduce the you will sample the inputs in some way. For example, you take the average of certain neighboring pixels and represent it as a single pixel. Like that, you can do for all the entire image, so that you can reduce the number of. Or you can do what is known as max pooling, where for a set of inputs, you take the maximum. Like that, you do for the entire image, entire inputs, and you will get a downsampled. So this why we do pooling or subsampling? It is to so otherwise the amount of data which we have to operate is very huge. That is one thing, and we want to do the downsampling so that the next convolution layer is going to focus on a different set of features. So if the convolution layer is going to repeatedly work on the same size images, there is going to be a repetition in the learning. Instead, once you downsample and reduce the image, it will be focusing on a different set of features. So that is basically the idea. Coming to fully connected layer, what is a fully connected layer? It is something which we saw earlier. It is nothing but the normal neural network where each input is multiplied with a weight and connected to the output. So each output will be connected to all the inputs from the previous layer. So for example, if your input is 3072 pixels, and you have 10 outputs, so each output will have will be connected to the 3072 inputs. So each of these inputs will be multiplied with a weight. So each output will have 3072 weights. Like that, 10 outputs you have 10 into 3072 weights. So fully connected layer, the number of parameters involved is going to be very high. So if you consider an example, this is one of the earliest proposed convolutional neural network, which is the ALEXNet, proposed in 2012. So if you see, you have the input, which is 224 by 224 into 3. 3 is RGB. The first layer is a convolution layer. It has, I think, 5 by 5 uh, into 96 sorry, 11 by 11 filter with how many channels? 96 channels. Then you have a pooling layer which will do the subsampling. So it takes it will sample 5 by 5. Each sample is taken from a 5 by 5 portion of the output from the first layer. You have the second convolution layer where another filter is applied, then the third convolution layer, like that. In between, you will have the activation functions, which is also not shown here. So you have these, how many convolution layers? You have 5 convolution layers, and in between, you have the pooling layers. So then finally, you will have 3 dense layers or fully connected layers. So this is how the ALEXNet is. And important thing to note here is the number of parameters is going to be huge. What do you mean by parameters? Parameters are nothing but the weights. So you have around 6 million parameters, uh, 6 million parameters in this network. So this is one of the oldest network I said. The number of parameters is too huge. Before we go further, I just want to make sure you understand the difference between training and inference. So I am going fast here because I assume many of these terms are familiar to you. Uh, so uh, so the neural networks involves two different phases. One is the training phase and the other is the inference phase. So what is training phase? In training phase, we just have an untrained neural network. What do you mean by untrained neural network? We have the network, but we don't know what the weights in the network are. And we feed the network with a set of training data. What do you mean by training data? If it is images, uh, and if it is these are images which may be marked with what type of objects are there in the image. So we are feeding this training data to the network, and the network will try to adjust the weight such that it is able to predict the output based on whatever the input is. So basically, if you are given an image of a cat, the algorithms for training, it will try to adjust the weight so that the output is also cat. So this is repeatedly done for a set of training data. And finally, we'll say the network is modeled or the is trained. And the trained model we can now use for our applications, which is what is known as the inference, where the trained model can be applied to new set of data. So we have already trained the model. Now, let's say you deploy it to uh, a surveillance camera, which will be continuously taking photos and giving it to the trained model, and the trained model has to identify what object is in this photo based on the training it has received. So this step is called the inference. So what are the tasks involved in inference? You have to fetch the inputs. So in the case where I mentioned, it is input from the camera. Weights are there. These inputs and weights have to be fetched to the inference engine. You have to perform some matrix multiplication operation. You have to apply some activation function, and then you get the output which has to be applied, right, written back to the storage. So in the later slides, we are going to focus on hardware for inference only. So why we focus only on inference? Because uh, see, one thing, training is done. In many cases, training is only once, but inference will be deployed for perpetually. So although we may have to retrain, but generally, if you see the number of times training is to be done is limited compared to the inference. Second, the inference we can run the training online or offline. It can be offline means you need not do the training on the device doing the inference. It can be done in some other system. For example, you can do it in the cloud. You can do it at some, you can take your own time to do the training. Whereas inference has to be, many a times has to be run on very low power devices, very resource constrained devices such as cell phones or security cameras, which have limited memory to store the models, etc. And these are the devices which are going to repeatedly do inference. So that is one reason why we are going to focus on accelerating inference. The third thing is the inference has to be very, the performance requirement for inference is very high because we need to run these inference very fast because the responses may be needed quickly. What are the metrics which we can use for comparing inference? Accuracy, obviously. What's the percentage of accuracy? How many failure or how many wrong predictions happen? Throughput, how many image, if we are talking in terms of images, how many images can be processed, or basically the frame rate which can be supported. So imagine the camera is continuously sending images. Your inference engine has to continuously scan these images or operate on these images and identify the object. So how much of how many images or how many computations can be done per second, that is throughput. Latency, many a case, so you give the image, after how much time you get the result. Model size, basically the size of the network. if you have a large network, it may not fit into the devices which are running the inference. Energy use, obviously, that is also important, and finally, cost. So, looking at some of the popular DNN models, these are not the later ones, the older ones. If you see, each of these deep neural network or convolution networks have many convolution layers, and the weights, if you see, so LeNet has 60K, whereas if you look at VGG16, it has something like 138 millions of weights. And operations, the basic operation here is going to be multiply and accumulate. We'll see why multiply and accumulate. But the number of operations are going to be too huge. Again, we have 15.5 giga operations in VGG16. So looking at this, we can understand that the weights which have to be stored is too huge. Obviously the inputs which are coming, they are images. They also have lot of data. The operations which have to be done, giga operations have to be done in a very limited time. So you need, there are a lot of computations and lot of memory involved. So you need powerful processing unit, and you need high bandwidth, large size memory. So what is the basic operation which is multiply and accumulate, and why multiply and accumulate? As I said, we are going to get the input, which we call as activation here. So activations are inputs from the previous layer. So you multiply the activation with the weight. You add with other weights, or so you have to do this repeatedly for different activations. So partial sum is the sum which is generated earlier by a previous weight and activation. So basically you have to multiply the weight with the activation and add to the previous partial sum to generate the current partial. So this MAC, or multiply and accumulate, is going to be the basic compute unit in our neural network. So hope I am audible. I just want to make sure. Uh, uh,
Yes, yes.
Yes, sir. You are audible, sir. You are audible.
Yeah. Yeah, thank you. So just wanted to make sure that I'm just going on talking. If you have any doubts or queries, you can either share in the WhatsApp, sorry, in the chat box, or you can also raise it. Okay, so we have this MAC operations, and what are the most common devices on which these neural networks are deployed are what are known as the GPUs. You might have heard the news of how the GPU market is exploding because of the explosion of AI. Why GPUs? GPUs have so the deep learning models, they have millions of parallel operations. GPUs have thousands of cores. Deep learning is mainly uses matrix operations. GPUs are built for SIMD operations, which matrix operations can be mapped to SIMD very cleanly. Deep learning generally for higher accuracy, it needs floating point operation. GPUs have floating point support, and large memory bandwidth is required. Again, the GDDR interface of GPUs support high bandwidth. So if you see here, uh, you can see that what it shows is different networks, the parameters in the network, and the memory utilization of a GPU. I just wanted to show this to you. So you can see that when obviously when there are more parameters, the GPU utilization also increases. But what the GPU is able to support around 1600 MB of memory for this VGG model. So basically GPUs can support this high memory, high bandwidth memory, which is required for neural network. Coming to the throughput which is available. So you can see that obviously there are each network has its own strength. So here what we see is consider this RESTnet, which is a popular network. You can see that there is some RESTnet 101, RESTnet 50, RESTnet 34, RESTnet 18, etc. So basically, this denotes the number of layers. I can say is the number of layers in RESTnet. There are other differences also, but mainly. So as the number of layers reduces, obviously the accuracy is going to reduce, but the number of computations are going to reduce. So you can have higher throughput. So you can see that the accuracy, for example, this Senate, which has very high accuracy, but the computations are more, you are not able to get a very high throughput. But with models like AlexNet, etc., the accuracy is only some 55 to 60%, but you are able to get frames per second. So almost 1,000 frames per second can be you can able to achieve in this particular GPU, which is an older GPU, Titan XP GPU. Compared to that, again, Jetson, which is an embedded platform for with GPU, you can say. It is a platform, it is with a lower footprint. So here, obviously, you won't be able to get the same throughput as high-end GPU as Titan XP. The throughput reduces to what around 100 frames per second, and but even then, you can get accuracy. Only thing is, you can get the accuracy similar to the Titan, but the throughput is around 1/10. You can see that you can get high throughput and good accuracy with GPUs. But the problem is energy efficiency. So you can see that here what this shows is energy consumption of AlexNet and OFIT. These are two different earlier neural network on K20, which is the Kepler 20 GPU, the Titan X GPU, and a CPU. And what it shows is you don't. The summary here is the power. You can see it is around 200 250 watts of power is required for most all of these applications. So you can see that most of the power, if you see the orange indicates the energy or the power for the orange indicates the convolution the energy spent for convolutions. So that dominates the total power. So most of the power is in convolution because convolutions are there are many convolution layers. Although there are only very few parameters, the operations are going to be huge. There are many such convolution layers. And so that is why most of the energy is for convolution, followed by the fully connected layer. The pooling and the ReLU energy is very less. But see, the power required is 250 watts, which is not something which can be afforded for a device sitting on the edge. So why such high energy? Because GPUs they support this massive parallelism. So many cores are running in parallel. It supports this high. So whatever strength we said of GPUs, it becomes a weakness when we look at the energy point of view. Then also CNNs, you need lots of data movement because see these inputs coming, they have to be multiplied by the weights, all the weights. We have this millions of parameters. All of them cannot reside in the GPU core. They have to be moved from the memory to the core, and this all these data movement it will take a lot of energy. And GPUs obviously they are not built for this particular, they are built for other purposes, and it is fitted to work with. So because of all these reasons, the energy efficiency of the GPU is very low. So if you compare different hardware platforms, you can see that the performance is giga operations per second power and giga operations per second per watt. So basically, if you look at the performance, you have 294 from a GPU. You have from a CPU, which is only very less performance. But if you look at the power, the GPU takes around 220 watts. Now, if you look at an ASIC, which is so this is for a new flow is a architecture, a convolution neural network architecture, which was implemented both on Xilinx Vertex 6 FPGA and as an ASIC. So if you see, it can, as per their claim, you can get a performance around 5 times that of the, or 4 times that of the GPU at a power which is around 1 by 20 or 1 by 40 times that of the GPU. So the operations per watt of power is too huge. The gap is too huge. So this is why we need to go for specialized hardware. We can run everything on GPU, but the problem is this is going to take a lot of power or energy, and to get energy efficiency without losing on performance and accuracy, we need to go for specialized hardware. So we will see what are some of the ways in which these hardware can do some optimization to. So as I said, the main problem with this convolution neural network is like there is lot of data movement involved. So just to recall, as I said, we have these convolution layers and the fully connected layers. The convolution layers will have some filters. We will do convolution between the filters and the input map to generate the output. In the fully connected layer, we have the input and the weights. Each input will be multiplied with all the inputs are connected to the outputs in the fully connected layer. It is an end-to-end connection between all neurons. You have large number of weights, but convolution layer, the number of weights is less, but you have many such many such filters, and you have too many operations in the convolution. So, how to build a hardware for this? Obviously, the amount of computations, it is in the mega, the millions of computations or giga operations per second. So you cannot have Mac for each of this. Instead, you will have to share the computations between these units. So basically, we will have, if you are looking at architectures for accelerating convolution neural network, you will have a set of P's or processing elements. What are these P's? In a basic form, they can be as small as a multiply and accumulator. You can have large number of such P's. So since Mac is a very small operation, you can have many such P's, but obviously you cannot have infinitely many. So there is going to be some limitation. And they are typically arranged as a 2D matrix. You can also arrange as 1D. So it depends on how you are. But what you need to understand is you have so many P's, and these operations are going to be mapped to the P's. Memory is going to be, and there is going to be a memory which is sitting outside, which will store the inputs, which will store the weights, and which will store the partially computed outputs. So you get the input, multiply by the weight, you get the output. That output has to be stored. So inputs, weights, and output has to be in the memory, and you need to transfer this between the memory and the P. So obviously, this memory access becomes a bottleneck, both in terms of the bandwidth required and also in terms of the energy. So what you can do, what we always do when you have such a high memory bandwidth requirement, we will introduce some local memory. We also introduce an on-chip network. Why do we introduce on-chip network? So that the output from one of the PE, we don't have to store it back to the memory. Instead, we can pass it on to the next PE so that it can do the rest of the computation and add to the partial sum and pass it to the next. So to facilitate communication between the P's, we introduce this on-chip network also. It moves data between the P's and the memory for use. And each of these P's, we can also add some local memory, a small local memory, so that the data in between or data can be stored in the local memory for reuse. So what are the different reuse strategies? So there are mainly 3 strategies and one which doesn't use the reuse. It is called, excuse me, 1 second. Yeah. So we have weight stationary strategy: output stationary, row stationary, and no local reuse. So in weight stationary, we will try to maximize the reuse of local weights. So basically, we will try to minimize movement of weights. So we will try to bring the weights to the PE and keep it there and use these weights on many different things. In output stationary, we will try to maximize the reuse of local partial sums. In row stationary, we will try to maximize many different type of reuses. And in no local reuse, we will avoid this register file. Instead, we will store everything in a global buffer and try to access from there. So let's see what is this weight stationary. We will keep the weights in the PE register file. For example, here you can see that we have 8 PEs. Each of these PE will have a weight or W0, W1, like that, W7. And we will, so the activation, which are the inputs, we will bring it from the global buffer or the memory. And we will pass on these inputs to all the PEs. See, remember, each input has to be multiplied with the weight. Okay, so in order to generate a partial sum, you need an input to be multiplied with the weight. So you will have each weight needs to be multiplied. You can look at the computation earlier. So each input may need to be multiplied with the each weight also. So for that, we will pass on the inputs to the weight. So for each PE will have its own set of weights, which need not be moved. So these weights are stored in the local register file. Inputs come in, a series of inputs come in. The outputs from the first PE, we will pass on to the next PE, which will add. So basically, you have the input partial sum, which is from the previous row. You add it to the current operation, pass it on to the next PE, which will add it to its own operation, like that, and finally the partial sum is stored back. So this is one example where. What have this achieved? Here we have reduced the movement of weights. We are trying to reuse the weights for each input, so that we don't have to move the weights between the memory and the PE. This reduces the bandwidth. This reduces the energy. Similarly, in output stationary, as I said, we will keep the partial sums inside the PE. So instead of keeping the weights, we will have the partial sums. So the weights will again be moved from the global buffer. The inputs will be moved from the global buffer. So input come to the first PE, the weights are multiplied with the input, a partial sum is generated, the inputs are passed on to the next PE. So so each PE now operates on a small portion of the output. Okay, so the output is split between the PEs. So each portion of the output will be operated by a particular PE. So remember, this is it might seem very simple, but remember that here we are showing only 8 PEs, but there may be more PEs, and we have millions of weights and millions of many inputs, outputs, etc. So when I say partial sum P0 is stored, it is not just one output, it may be a set of outputs which are stored, a set of weights are brought. So remember, this has to scale. Okay, so now what about row stationary? Here we loads of so here what we do is we keep as much related to the same filter row. So basically we will look at the operation in terms of the filter row. So so for example, you have this filter ABC, this filter, it's first row ABC. It has to be, so if you see, this ABC has to be multiplied with the first column, right? That is one operation you need. So if you see, the first row will be given to the first PE, and any input which needs to be multiplied with the first row will be passed to the first PE, and the output will be stored there. So here the reuse is not in terms of PE. Instead, there will be reuse across the different PEs. So basically, you bring the data here. The reuse is not limited to just one PE. Instead, the same data will be used in multiple PEs. So although the reuse is limited in a single PE, but from the memory, if you look, there is going to be lot of reuse. And finally, we have another option where you don't have any reuse. You have a global buffer. You don't bother about any of these reuse. All the weight, activation, and the partial sum you try to bring. Instead of distributed register file, what's the advantage with this? See, if you need, the P's become very small here. P's are just multiply and accumulate. You don't need much of a register files here. Most of the that area can be used to build the memory. So that's the idea. Okay. Now we said the net on-chip network is required. But what is the problem with an on-chip network? Again, it is going to take some resources. So this is an example for one particular neural network, which is Iris architecture. So what this shows is the relative area in which each of this resource takes. So the P you can see is of size here, which is fixed for Iris. The on-chip network, if you don't have a network, instead you have a bus with all the P's are directly connected to the bus. Obviously, the area required for the bus is very less. Instead, if you have an NOC and you have a mesh type connection, your size is going to be higher. And if you have a crossbar switch as the NOC, that is every PE can connect to any other PE, then the area which it takes is going to be huge. But what is the advantage? As you move from bus to mesh to the crossbar, your throughput increases, but obviously along with the area, the energy is going to. So you have to take a judicial judicially choose one of these. We have a session on NOC. Hopefully, we'll address about this in that session. What about power efficiency? So, if you to compare the energy required for data movement. So, if you see here, what it shows is, if this is the relative energy movement if the data is stored in different areas of the of your system. So, for example, the reference is ALU. Obviously, we take the ALU as the reference. So, if ALU is 1 and if you have register file, the amount of energy, if you want to take the data from the register file and operate in the ALU, there is not going to be much difference. But if you want to take the data from another PE, you will have to spend 3 times the energy. If you want to take from a global buffer, you need to spend 10 times energy. If you want to take the data from the DRAM to the ALU, you have around 500 times energy. So you can understand that why minimizing the data movement is important. So the earlier strategies which we have mentioned, it will try to address this by having local register files and reduce the data movement and reduce the cost. If you look at normalized energy per MAC for different strategies which we have mentioned, WS is weight sharing, output sharing, 3 different output sharing, no sharing, and finally row sharing. So if you see here, the energy is maximum for the no sharing, which is to be expected. But why people go for this? There are other optimizations which are possible, which can reduce this. But the row sharing, where you have maximum reuse between PUs, gives the best in terms of energy. And most of the energy, so the energy distribution is also interesting. So if you see in terms of the NOC energy, it is very less for the row sharing because probably because now the P's are sharing the data. So the data transfer happens between the neighboring P's. So that may be the reason. I am not very clear why it is. But the register file, the memory, the power dissipated by the register file is higher there. So this gives some interesting aspects about how the different strategies work. So coming to very common or popular architecture, which is the tensor processing unit. I'll just briefly introduce this to show you that this is so whatever we have talked, that is exactly what is going to be implemented. So we said the basic unit is going to be a matrix multiply unit. So in addition to this matrix multiply unit, they are set up as a systolic array, and the TPU is like a coprocessor which sits to a PCI, so it can interface to the other processors connected to a PCI interface. This has a CISC-based instruction set, and there are these aspects. So basically, what happens is yeah. So what happens is you fetch the input and the weights. Input will be from the CPU host memory to this buffer. The local activation storage, it stores the input. The weights are from the DRAM. It is stored in the weight FIFO. And these two are brought to the matrix multiply unit, and large scale matrix multiplication is done. And then activation function has to be applied. So remember, convolution is not just the matrix multiplication. After that, you need to do a non-linear activation. So this activation layer, the block that will perform the activation function, and the output is returned back to the local buffer. So basically, this is actually here, the P's are themselves not storing. Instead, it follows the last strategy which we mentioned, no sharing. Instead, data is stored into the unified buffer here. That is what they have used. So you can see here comparison between TPU and a AIT GPU. So you can see that the ratio for various neural networks, the TPU shows around 16.7 times the performance of GPU. So different numbers you can see. On an average, you can say more than 10 times improvement compared to this particular GPU. So, and what about performance per watt? 17 to 34 was what is being reported. So, related to the base. Okay. So, so that is about one common architecture, and these are some of the architectural innovations you can do. Coming to algorithmic optimization. So see, as I said, the problem is we have loads of these parameters and loads of comparisons. Instead of focusing only on architecture, we can do some optimizations on the algorithm level. So what are some of these optimizations? Okay. So one second. Sorry. By the chat. Yeah. So there are various algorithmic optimizations available. Some of them you might have heard about: model compression, weight sharing, pruning, quantization. There are some ways to compress the model itself, and then there are some computation reduction approach also. Okay, so the slides are moving very slow. Sorry for that. Okay, yeah. So model compression, what does that mean? See, the problem is we have a large model. One way to address that is you compress the model. For example, people have suggested applying Huffman coding to compress the model so that it can be stored very efficiently in the memory, and transfer, instead of transferring the uncompressed model from the memory, you transfer the compressed model, which will take less bandwidth, which will take less energy. But what is the disadvantage? So when you have a compressed model, you finally, when you do the operation, you have to decompress. Okay, so that is the problem. So that decompression is going to take some computation. So again, this is a trade-off. should we include a decompression unit so that the compressed model, the savings from the compressed model is higher when compared to whatever is resources and energy is required for the decompression. Then another way is to use better compression, some lossy compression also. But the problem with lossy compression is we are compressing the weights. The weights are, sorry, pardon me. Yeah. So we are compressing the weights, and if we have a lossy compression, obviously the learned weights are going to be affected, which means it is going to affect the network itself. So what we will do? So we will do a lossy compression, but with the compression, we retrain the model itself so that the weights are adjusted with compression also taken care. So this is called fine tuning, and then you have a compressed model that also has been applied. So lossy compression, if applied, can lead to loss of accuracy. You do a retraining to improve the accuracy. Okay. So that is one thing. Second is weight sharing. So in weight sharing, what we do is many of these layers will have the same weights. So this is again not very commonly used. So basically, any common weights you are going to use only single weights. So for example, here between the first and the second layer, distinct weights are only two: W11 and W34. All other weights are having values very close to this W11 and W34. So instead of you storing distinct weight for each of this, you store only these two weights. So remember, we are looking at millions of weights. So from having to store only two weights out of 8 is a significant saving. Okay. Then connections from the network.
What happened, sir?
I think he got disconnected. Can you just wait for 2 minutes?
Sure.
Nalesh will be joining soon. Just a couple of minutes, a technical glitch. ഇവിടെ കിടന്നു സംസാരിക്കുന്നു
Is my screen visible and am I audible?
Yes, yes, Nalesh.
Sorry for that disruption. So there was some issue with my network. Sorry for that. Yeah, so we were talking about pruning. So pruning, as I mentioned, we will try to compress the network by removing all the connections which are insignificant in terms of the actual value. Then next optimization we have is what is known as quantization. So here what we do is originally neural networks were using floating point operations, but floating point, as you know, is very expensive. Instead, we can uh, uh, lower the precision of this weights and the inputs and use, instead of floating points, we can use lower precision, for example, integers. So what this will help us, one, the models become smaller because now we are not using this 32-bit floating point. Instead, we can use 16-bit integers, 8-bit integers, etc. The operations also, instead of floating point operations, we can use fixed point operations. So here what you can see here is different types of quantizations and how much of size reduction. So you can even get up to 75% reduction in the size. So I will skip this so that we are able to complete. Then what are some of the platforms support which are available for these optimization? The TensorFlow from Google itself, it has something called TensorRT, which which you can use to get all these optimizations done. You can do pruning, you can do quantization, etc. So here what you can see here is in the table different networks. You can see that a floating point 32 and integer rate quantized model. So you can see that, for example, ResNet 50, 72.9% accuracy for floating point 32. Integer rate, it is only, the accuracy just drops to only 72.84. That is, there is not much difference. But the difference in computations and difference in memory bandwidth is huge. So this is the idea behind quantization. Then another way to do is, instead of using networks like VGG, GoogleNet, etc., we use optimized networks. You have what are known as YOLO, RCN, and SSD, etc., which are our mobile net, SKUSnet, etc., which are lightweight networks optimized for mainly for mobile and resource constrained applications. You can also go for that. What these models do is, what these networks do is, they trade accuracy for the computation. So basically, you try to reduce the model size, reduce the computation. You have some hit in accuracy, but again, it is not that much when compared to the savings you are making. Then I'll skip this. Another way is to go for what is known as knowledge distillation. So here again, we are trying to get a smaller model or a smaller network. But instead of starting with a smaller network, we will have a full-fledged network, which we call as the teacher network. And we will have a smaller student network. Once the teacher network is trained, the student network will try to mimic the teacher network to get the output. So I won't go into the detail, but knowledge distillation is another option where you can use this technique to reduce a full-fledged model to a or network to a smaller network, so that your computations can be reduced. Then this is another option. You directly apply on the computation. So I won't spend too much time. I think this will be taken in the next session. I know that. So I'll skip this. So there are options of, instead of using you performing matrix multiplication directly, you do some FFT operations to reduce the complexity of the multiplication. Then another option is what is known as the Vinograd transformation. Again, I'll skip this. This will be addressed in the later on session. Okay, so now coming to some of the platforms which are available, one of the most commonly available platform is FPGAs. Now, the later versions of all FPGAs, they directly support, have support for this deep neural network applications. For example, Xilinx, they have what are known as Versal A cores. They have Vitis, their software platform, which is the Vitis. It has some Vitis AI toolkit also, which actually supports all these different optimizations which I mentioned, like pruning, fine tuning, quantization, etc. So that you can take a dense neural network, do all these optimizations, get a very compressed network, and deploy it on the FPGA. So as I mentioned, these platforms support different frameworks like Caffe, PyTorch, etc. Coming to hardware, we have the FPGA itself. We have something called the DPU, which is an IP which is optimized for, which is meant for deep neural network. Or basically, it is deep neural network processing unit. So whatever models which are generated in the previous step, they can be deployed directly to the DPUs. And one example which is done by one of my students. So here she has done a ResNet 50 model on Xilinx FPGA using these different strategies which we mentioned earlier. So compared to a PC, you can see that the time required. So the time on the PC was around 1430 milliseconds, which was reduced to 16 milliseconds on the FPGA. So very this is not something very I just wanted to show that this is possible. Okay. So until now we have been talking about the various traditional platforms or traditional computing paradigms which we were using. But one problem with all this is, as I mentioned, the main issue here is the transfer of data between the memory and the processing unit. It is energy consuming. It is taking too much of latency, too much of delay, too much high bandwidth is required. So this is one of the main bottleneck which limits the improvement in performance and energy efficiency for a neural network. So what we call this the traditional non-human architecture, where you have the memory separate and the processing separate, and the transfer of data between the memory and the processor is the bottleneck. So in order to address this, some newer technique. So when, for example, if you compare with our brain, the brain doesn't have a separate block like memory and separate block like compute. So the memory and the processing, everything happens in the neuron itself. Okay. So mimicking this, we have the something known as compute in memory, where we try to do computations and processing in the same unit itself. So the basic, again, we will have later on sessions. I just wanted to introduce you to this. So one of the basic unit for computing memory is a crossbar. So we use so these crossbars are built using newer devices like memristors or spintronic devices or phase change memory devices. So what are these crossbars? So basically what we need was, we need some input which has to be multiplied by a weight, and you need to add up all this to get a output. In a memristor, the conductivity of the memristor is the weight, we call it. So each memristor, its conductivity can be programmed earlier. So you have G1 conductivity for the first, G2 for the second, G3, Gi for the last. So you apply the input as voltage. So the resultant current will be V1 G1 plus V2 G2 plus V3 G3. And you get the current is nothing but a multiply and accumulate operation of all these inputs with the weight. So this is the idea. So how do you arrange this? You have what is known as this crossbar architecture, where you have inputs coming from the left side, you have outputs on the bottom. Each of these intersection is a memristor. So if you see the first memristor will have G1, this one will have G2, this one will have G3. V1 G1 plus V2 G2 plus V3 G3 will be, you will get the input for input as a the output as a current. So you can, in parallel, you can give all these inputs. You can get you store a different sets of weight in the first column. You will get a different output from the first column. So similarly, in parallel, you can get many different operations together. So so and here the thing is, we don't have to bring the weights from somewhere else. The weights are already part of the memristor itself. So this is the idea behind the computing memory. So I won't talk more about this, because we have sessions ahead on this. For example, in 2023, IBM proposed something called an analog chip, which is based on phase change memory based crossbar network. So it has around 10 plus millions of synapses. It supports 10 raised to 4 GOPS per watt. That is 1000 operations per watt. Remember the previous. So let's go back and just see how it compares with whatever we were looking at the other platforms. Sorry for going back. So if you see the GOPS which were supported in those platforms are only, the maximum we got was from this particular ASIC, which is 230. Whereas 10 raised to 4 is 10,000, right? 10,000 GOPS per watt. IBM claims to have gained with this architecture. So that is one future direction where we use these newer or novel devices to have these crossbar arrays, which can be used for this matrix operation. So with that, I'll conclude my talk. So please consider this as only an introductory talk. I am sure that many of the things may not be clear for you. Hopefully, this act as a introductory session. There are a couple of sessions later which will add on to this. And if you have any more doubts, you can contact me. If you have any queries now, I'll address that. I think there was a query, but unfortunately, after I disconnected, I can't see that earlier message. If someone can read that, it will be helpful.
The query is for improving my model as best to classify my samples, which way we can use. It's from Sendil.
No, actually, yeah. So it is nothing to do with improving the classification performance. It is to do with how effectively you can build an architecture for that. See, the accuracy improvement all happens during training phase. So here we are trying to build a accelerator which performs this inference, and that accelerator has to be very efficient in terms of the the performance, in terms of throughput, in terms of latency, in terms of energy consumption. So I don't think the improving the model performance is something related to this. I think this question was raised when I was discussing the different strategies of reuse. Hope this addresses your query. Any other question?
Nalesh, I think there is no question.
Yeah. So with this, we will conclude the session. Sorry for that disturbance in between. So I will be sharing feedback for both the session. This will be done through the WhatsApp or by mail. And attendance, as I mentioned, it will be taken through the Zoom direct. Okay. So we will conclude today's session. We will meet tomorrow at 6:30 for the next session. Thank you.